Yo, 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 what up, St. Matthews Elementary? S.T.E.A.M Chemist here, back with another explosive science show. Today, we are going to explore the realms of science, technology, engineering, art, and mathematics. Now remember, do not attempt to do anything you see on this show. It is very dangerous. And I have been trained to do all the experiments that you're about to see. Also, safe science. Safety is very important. So you're going to learn a lot about safety, and we're going to learn a lot about reactions today because we are going to do some explosive science experiments. Let's get started. Let's start with this experiment. This right here is just a water container. A lot of times we see this upside down with the water cooler. You push the button and the water comes out in your cup and you drink it. Yeah, but today we are going to transform this into a rocket. Whoosh! It's going to whoosh. But we're going to do this safely. We are going to first talk about gases. Everybody say gas. Gas. So gases exist all around us. They take up a lot of the space in between a lot of these big solids and liquids that are also around us in the world. So gases are very, very fast. Fast molecules, they bounce around, and they push each other all over the place, and they just really, really are active. So I'll show you an example of how active gases are. So I just inhaled and exhaled some gas. So there are different types of gases. One gas you all are familiar with is oxygen. Everybody say oxygen. Also, another gas is carbon dioxide. Everybody say carbon dioxide. Carbon dioxide. Carbon dioxide is the gas that we breathe out. Also, the gas that was in that balloon. So we breathe in oxygen. We get it from the trees. And carbon dioxide, we breathe that out. Try it. Breathe on your hand. You can feel that gas. That's the same gas that's inside of this balloon. And I can tie this balloon just like so. And inside the gas is trapped, as you can see. And this gas isn't going anywhere unless we pop the balloon or there's a little hole. I'll show you. And put a little hole in there and then look, the balloon shrinks because there's a little hole in there and the gas was able to escape. Similar to this container right here, which brings me to my next experiment. First, very, very, very important, we have to practice safe science. So I'm going to put on my rubber gloves. These gloves are going to keep me safe because we are going to be using methanol. Methanol is an alcohol that is very, 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 very tiny. Tiny. That means that it takes up a lot of space when it's vaporized, if you would. So what we're going to do is vaporize it. But first, we can't just vaporize it as it is as a liquid. We have to put some energy into it. Some energy. Everybody say energy. Energy. So we're going to take some of this and I'll put it here in my cup, just like so. It's always important that you pour directly from one container into the next. I could have poured it in here, but that's not scientific at all. I always have to use a second container. So now we'll take this here and inside it goes. Boom. Just like that. So now it's a liquid. So we have liquid in there, but we want to vaporize it. So to make sure that we can vaporize it, we have to turn it into smaller, tiny particles, just like this. So we shake it. We shake it. And every time we shake it, we are busting up that liquid into tiny, smaller pieces that will then be floating all through this container, but we can't see those tiny vapors. Similar to the vapors that's inside of this room right now. Between me and this camera, there's small water vapor inside of our room. Inside the room, rather. So the more that I shake it, the more energy I give it, the more that I break down this liquid into smaller, tiny pieces that are floating around about inside of my container. Let's give it another shake. Shake. All right. Now we don't need the rest of this liquid, so I'll pour that liquid on out. And there we go. So notice I have my hand on the top of this because I don't want those vapors to get out of this container just yet. Switch hands because I'm right-handed. And we are going to light these vapors on fire. And to do so, we need to make sure that we're knowing about the fire triangle. The fire triangle is a spark of heat or some type of heat, some food or fuel, and then oxygen. Oxygen. Oh, we love oxygen. So oxygen and fuel and some type of heat. Those are the three things we need for a fire to exist. So oxygen exists. Oxygen exists inside of this room. Here's our heat and our spark. Our fuel is right there, down in our container, right here, right there. So here we go. It's gonna be like a whoosh, like a rocket ship going off. I'm gonna keep it on my table because I don't want it flying around the room. All right, here we go. In 3, 2, 1. Whoosh! Oh, I love science. And then afterwards, you have a little afterburner because there is some type of heat still reminiscing in there, and the extra vapors are still trying to fly out. If you would, as you saw, oh goodness. But also inside of here is carbon dioxide and water. So I know you're like, do it again, do it again. I would be able to do it again, but I have to make sure that all this carbon dioxide that was created after burning off all this methanol gets out as well. And this is a tiny, tiny exit, and there's a lot of carbon dioxide in there. However, some of this water, which is also another byproduct, is in there, and there we go. Water. Whoosh battle! Next experiment. Next experiment. So this right here is an Erlenmeyer flask. And this is a great, great container for our next experiment, our next reaction. This reaction is famously called elephant's toothpaste. Elephant's toothpaste. Woohoo! So elephant's toothpaste is a decomposition reaction. Try to say that word. Decomposition. Decomposition. So decomposition means to decompose or to break down. And what we're going to do is break down our hydrogen peroxide. Hydrogen peroxide. So hydrogen peroxide right here. This is my hydrogen peroxide. This is a stronger version than the typical hydrogen peroxide that you see at Walmart or a drugstore, at a pharmacy. This hydrogen peroxide is 30%. And this one right here is 35%. So this one's stronger. So we have 30 and 35%. You all are used to 3%. And 3% is a very, 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 very diluted mixture of hydrogen peroxide. If we were to have 100% hydrogen peroxide, that would be extremely dangerous because hydrogen peroxide is a corrosive liquid. It breaks down and it burns and it eats through things. And what we're going to see today is how it decomposes also naturally. But we can speed that reaction up. So hydrogen peroxide exists, and then as I open it and expose it to the air, it breaks down into two things: water and oxygen gas. Oxygen gas that we are used to. We're used to breathing it in all the time. This naturally will turn into water and oxygen gas, but it takes a long time for that to happen. If I was to want this amount right here to evaporate and turn into water and all the oxygen bubbles evaporate out of it, it would take about 6 months for this little bitty amount. But in science, we have things called catalysts. Everybody say catalyst, catalyst. So a catalyst speeds up the reaction. And what we're going to do is speed up this decomposition reaction. First, let's build our catalyst base. So here we have our water and some soap and our potassium permanganate. I want to show you how liquids disperse and other liquid. So let me get some water here. There you go, water. And here's some food color, and I just want to show you the difference. So this is a liquid inside of a liquid, boop, and you can see it slowly mixes in and takes all the color of the blue some time to drop down to the bottom and mix in with the rest of the water. Now, my glove broke. So now let's take some of our potassium permanganate solid and sprinkle some in here like so. I want to make sure we get a nice amount because we want this reaction to be very explosive. So let's take this and cover it up. Now, we don't want our peroxide in there just yet because it would expand and it would bubble and we wouldn't have anything in there to trap those bubbles because remember, oxygen is a gas and our liquid that's going to be remaining is going to be a water. But to trap those gas bubbles, we'll take some soap and insert some soap. Just like so. And then we want to get some water in there and get that nice and mixed up well. Just like that. And with the stirring action, we can get that nice and mixed even more. And boom, just like that. Now, here comes the fun part. What we're going to do is take some of our hydrogen peroxide and pour it in our container here because this reaction is going to happen very fast. I'll push it a little forward so it doesn't splash on me, you know. So here we go. All right, and remember, this is a decomposition reaction. It's going to decompose our hydrogen peroxide into water and oxygen gas. Our oxygen gas is going to be like foam and suds. It's going to be hot and steamy because remember, we are breaking these bonds up and it's going to create some heat or some energy. All right, move this out of the way. Here we go. In 3, 2, 1. Ha! Whoosh. And it's very, very puffy. It's steaming. There we go. Steaming because it has a lot of heat. And then, of course, when we warm up water, it boils and then it steams. So that's what you see here. All of this steam is water vapor, similar to our vapors that we had from our previous reaction. And of course, now you can see all the big fluff and all the bubbles that are trapped from our soap. And this is why they call it elephant's toothpaste because it's so foamy. It's like an elephant can come scoop up the trunk and brush your teeth. Elephant's toothpaste! Woo, nice and warm. Woo, nice and warm. So this next experiment is going to cool things down a little bit. We are going to learn about nitrogen. Everybody say nitrogen, nitrogen. Nitrogen is an element that is very abundant. That means there's a lot of it. It's all in this room. It's all outside. It's the most abundant element actually in the atmosphere. It's a gas that we are most prevalently seeing it or feeling it as the wind blows or as we breathe in. But nitrogen right here in liquid form. So this is my door and we're going to see nitrogen in liquid form. So it exists as a gas and a liquid. So remember, safety science. Put on my gloves here, pull out my container here. Let's get this open. So nitrogen is very, very cold as a liquid. And as a liquid, it cools things around it down also. So there we have it, liquid nitrogen, liquid nitrogen. And inside of there, you can see all of this steam or smoke. If you were here, you would blow into it and you could see and feel all of that condensation. This is condensed water and gases that exist in the air already. And when I blow into it, the gas shoots back up at my face like an explosion. Feels so good. Now, if I take these balloons and I stick a balloon in there, look at what happens to the balloon. The balloon goes down and down deeper into my container, but check it out. It doesn't look like it's full of air anymore. But here, let's take a look. Just put another one in there and another one in there. So what you're seeing here, I'll leave this one out so you can see it. The gases that exist inside this balloon are getting very cold and condensing closer and closer together because they want to warm each other up. They want to stay warm because when they're warm, they can spread out and they have a lot of energy. But when it's cold, it slows down their energy, so they kind of get closer and closer and condense and cuddle up and huddle up to keep their energy and preserve their warmth. So that's what you're seeing as it gets down deeper and deeper into this frigid, cold environment. It's negative 321 degrees Fahrenheit, the liquid is. So if I was to take some of that liquid, put it in my cup, look at it now. It's boiling because it's so hot outside of this room or outside of this container. And it's boiling still because in this room it's so hot and it's evaporating. Everybody say evaporate. Evaporate. That's what we're seeing here. That liquid is boiling and turning into a gas. So there we have it there, liquid. And I'll show you, it's turning into a gas by popping that lid off. There we go. See, look at that. Pop, 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 pop. Pop, 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 pop. And it'll keep going on and on and on and on because all that liquid is turning and churning and churning and turning into gas. That's what's building up the pressure right here. And pop, pop goes the lid because all that liquid that I just poured out is turning into gas. Now that I poured out all that liquid and I put the container on, nothing happens, right? Because none of that liquid is in there turning into a gas. And the gas that does exist in there doesn't expand until I squeeze it and then pop goes the lid, just like so. Let's check on our balloons. So look at our balloons now. Look at that. They're frozen. But look, as they warm up, they're growing, and they're growing, and they're growing. Whoa, look at that. Now, look at this. Look at that one. Slowly but surely, the balloons grew back to their normal size because it warmed up. And the way that they warmed up was releasing themselves from this cold environment. So in the cold, they got shrunk and condensed. But out here in the heat, they like to expand and grow. Remember from the first experiment, gases are very fast and move all over the place. So if I was to take this in, whoops, excuse my pig. Pop, pop. So that's the sound of all the gas escaping right at once. Pop. And inside of here is more gas. And we can see the differences of gas. The gas that's in here when I pop, look, we can't see that gas. But this cold gas, we can see that gas, can't we? Let's go to our next experiment. This next experiment requires our bucket, some water, a container, and a heat source. Oh, and of course, liquid nitrogen. But we'll get to that later. Now, what we're going to do is take some of this water and we're going to put it in our electric kettle. Inside of our electric kettle here, boom, this electric kettle plugs up to the wall, turning on water nice and hot, raising the temperature, perfect for our experiment. So we'll take it, put it on this right here, and plug her up. All right, now we're back, and you can see my water has transformed. And look, all the steam that you see coming out of it. That's because this water was just like our other experiments, giving heat and energy. And what that does is break down the bonds into smaller, tiny pieces a lot of times, ready for reactions. Now what we're going to do, take our water, and I'm going to pour it into this container here for an easier pour for our final explosion. Now that requires our bucket here, just like so. Let me get some nitrogen, liquid nitrogen. What we're going to do is evaporate. Everybody say evaporate! Evaporate! Evaporate this liquid nitrogen right here back into its natural gas. The gas that it wants to be. So inside of here is bubbling and bubbling and bubbling because liquid nitrogen would rather be a gas. It doesn't like to be a liquid. In liquid form, it's very, very antsy and bubbly and vigorous and dangerous. So what we're gonna do is help it out a little bit with some hot water. Also, a catalyst helps speed up this evaporation process because, of course, we know it's already evaporating from this container experiment that we did a second ago. All right, so for our final explosion, yes, our final explosion, we'll get a big countdown from 5. In 5, 4, 3, 2, 1. Woohoo! Now you can see it's bubbling and bubbling and churning. Woohoo! And you can play with it just like so. Awesome, awesome, awesome. Thank you, St. Matthew's Elementary. I appreciate you all. I hope you all enjoyed this explosive show. Can't wait to see you all in person next time. Thank you, and remember, peace, love, and science. Take care.